very, very honored to have the chance to participate in this conference on determinism versus free will to be held in the Galapagos, where I would so dearly love to come, but cannot. Just briefly, my wife died of pancreatic cancer 2 months ago, and I'm hiding on an island in South Carolina dealing with grief. But I'm thrilled to have the chance to talk to you all. I'm going to begin with a provocative statement. Maybe, just maybe, I have answers to the questions. And I hope that I can present the ideas to you. Carlos and his colleagues have an outline of the talk, the latest version of which is sent this morning. I hope that it's circulated and you will look at it and see whether I'm being silly or not silly. So I'm going to start with Cartesian dualism. All of our problems start with Descartes. As you all know, Descartes posed his famous res cogitans and res extensa in around 1650. Res cogitans is mind. It's thinking stuff. It's the experiential aspects of the world. It's I think, therefore I am. Res extensa is his mechanical world view. That non-mind, like the human body, is just a machine. So that's Cartesian dualism. Now, to see why it's always been a problem, I have to take us to Newton and tell us the foundations of what is in fact reductive materialism that starts with Newton and reaches a crescendo with Laplace. So we all know Newton's 3 laws of motion and universal gravitation. We know he invented the differential and the integral calculus. So if we were to ask Newton about billiard balls on a billiard table that are rolling, Sir Isaac, what will happen? Newton would say, please measure the initial positions and momenta of the balls, measure the boundary conditions, the edges of the billiard table, write my laws of motion, 3 laws of motion, in differential equation form among the balls. Those laws give the forces between the balls. Having done that, please integrate my equations, and that will give you the trajectories of the balls forever if we ignore friction. Later we can put it in. So I want to make 2 points about this. Integration is to deduce the consequences of the differential equation for the trajectories of the balls. So integration is in fact deduction. Now we all know from Greek syllogisms, Socrates is a man, all men are mortal, Socrates is a man, therefore Socrates is immortal. Deduction is such that the premises entail logically the conclusion. So integration by Newton, integrating Newton's differential equations, give you deduction, which gives you the entailed trajectories of the billiard balls. So Newton gives us the birth of determinism in modern classical physics, and the determinism is, his laws are time reversible and deterministic, and everything that can ever happen is entailed in the entailed trajectories of the balls. That's determinism. With Laplace, a century and a half later, who said, if we knew the positions and momenta of all the particles in the universe, using Newton's laws, we could deduce the entire future and past of the universe, or a giant computer in the sky could, called the Laplacian demon. We get the view of the becoming of the universe as completely entailed. It's entailed and deterministic. Quantum mechanics takes us further. It's still entailed, but it's no longer classical physics. So let's stick right now with classical physics. I'll come back to quantum mechanics later. And we get to the standard problem in the philosophy of mind, the two standard problems. The first problem is with Descartes' dualism, and it's the following. If the brain is a Newtonian-like classical physical dynamical system, like the billiard balls, then the current state of the brain is a sufficient condition to determine entirely the entailed next state of the brain. But then there's nothing for mind to do. It'd be like mind acting on the billiard balls. And furthermore, there's nothing for mind to do there either. And furthermore, not only is there nothing for mind to do, there's no way for mind to do it. Is mind supposed to make the billiard balls swerve on the table? And that statement is the core of the problem, the central problem in the philosophy of mind that nobody has answered since Descartes. One of the things I'm going to do today is propose an answer. Doing so requires going beyond classical physics. Within classical physics, there is no answer. The second problem has to do with free will, and I'll say it here and then come back to it. If I am a deterministic Newtonian dynamical system, my brain, whatever consciousness is, and I walk down the street and I pick up a frying pan and hit an old man on the head and kill him, I have no free will whatsoever. I'm entirely deterministic. Therefore, it's not my fault that I killed the old man with the frying pan. So I don't have a free will. To jump ahead, when we introduce quantum mechanics, things become ontologically indeterminate in single quantum measurements, like radioactive decay. Then we could have a free will. I walk down the street, I pick up the frying pan, well, a radioactive decay or some other quantum event happens in me that's indeterminate, and I smash the old man on the head. But since the quantum event is entirely random, I'm not responsible for it. It's just some random quantum event. So I could have something like a free will, but not a responsible free will. That kind of summarizes where we are on both determinism and free will. And even if we escape classical physics and go to quantum mechanics, our thinking that says, but you cannot have a responsible free will. Okay, now, I want to introduce something that's entirely new scientifically, that my friends and I think that we either invented or discovered 3 years ago, that I think allows us to answer Descartes' first problem, namely, there's nothing for mind to do and no way for it to do it. So I have to tell you a little bit about quantum mechanics, and then I'm going to tell you about a new discovery for which we've applied for patents. It's called we call it the poised realm. Okay, so first, just a word about quantum mechanics. We all know there's the Schrödinger equation, and it propagates waves, and it explains the famous two-slit experiment where you get the interference pattern by the interference of the Schrödinger waves as they pass through the two slits, and it cannot be explained by classical physics. Now, in quantum mechanics, nobody knows what's waving in the Schrödinger wave equation, but it works. Now, there's a phenomenon that's been studied. So the interference pattern, as I think everybody knows, is that even with a single photon, if it goes through the two slits, it makes a spot on the silver halide photodetector. And if you wait for 1,000,000 photons to go through the two slits over a period of a month, you get the famous interference light, dark, light, dark pattern on the screen. Therefore, each photon is behaving in such a way that it exhibits this funny property that gives rise to the interference pattern, not the set of photons. So this is true of a single photon. Okay. Now, in the past 20 years, one way of thinking about quantum mechanics and its relationship to the classical world, which is a very complex issue, is something known as decoherence for an open quantum system. An open quantum system is one that is a subset of the universe. And what's going on in decoherence is the following. For a closed quantum system, the quantum waves have at every point in time and space the waves have amplitudes like water waves, and at each point in time and space what's called phase information keeps track of the height of the wave as the wave wiggles up and down in time and space like a water wave, and it's called phase information. In decoherence for an open quantum system, and this is demonstrated experimentally, the phase information of the open quantum system is lost to the rest of the universe. And the two critical facts are the loss of the phase information is not causal at all. The phase information is just lost out into the rest of the universe. As the phase information is lost, the quantum waves don't know where their peaks and valleys are, and the interference pattern fades and approaches classicality ever more closely. It's called approaching classicality infinitely closely for all practical purposes. So that's decoherence. There's no doubt about it. It's known. I'm going to try to use decoherence and the poised realm, which I'm going to talk about next, to answer Descartes' problem about how mind can have consequences for brain, but they're not causal consequences. So I need to tell you this to try to get at how to answer Descartes' first problem. There's nothing for mind to do and no way for mind to do it. And I'll also need the same to tell you about a responsible free will. So here's the poised realm. It's based on the idea, it's a new idea, and it appears to be true, that systems can go back and forth between being quantum and classical for all practical purposes and being quantum again. They can, in English, hover reversibly between quantum and classical. So this is our poised realm. And I'll just tell you, it's parameterized by two axes. A y-axis, which is the degree of coherence. A fully quantum system is fully coherent, namely it has all the phase information. And in decoherence, phase information is lost as you go up the y-axis. But you can come back down the y-axis and become coherent again in two ways. By quantum measurement, certainly, and in theory and recent experiment, by injecting information. It's called Shor's theorem. If you have decohering quantum variables and inject information, they can become quantum coherent again. Shor's theorem. There's recent experimental work showing that a system that is decohering can become recoherent again too in light harvesting molecules. So that's the y-axis. The other axis is, the x-axis is ordered, critical, and chaotic, and it's turning out that the x-axis is real also. Some molecules are ordered, some are critical, and some are chaotic. And in quantum mechanics, criticality happens to be the metal insulator transition, where Anderson localization is just breaking down in a semiconductor. Okay, so now I've told you about the poised realm. Okay. Now I want to show you that the poised realm and reversible going from quantum to classical to quantum can answer the first problem with Descartes. There's nothing for mind to do and no way for it to do it. And the essential idea is the following. Suppose approximately that mind is somehow quantum and brain is somehow classical or classical for all practical purposes. Then mind, and I'll go into more detail later, can causally, without any causes at all, mind can decohere to become classical for all practical purposes. Therefore, mind can have consequences for brain. without ever acting on it causally, as in classical physics. Now, if that's right, we just have the first possible answer to Descartes that we've had since Descartes. And we've done it by leaving classical physics and embracing quantum mechanics. But that won't do us yet, because that only happens once. Via recoherence and decoherence and recoherence and decoherence and recoherence and decoherence in the poised realm, mind can repeatedly have consequences for brain. Therefore, mind can repeatedly have consequences for classical behavior. So we've answered, in principle, Descartes' first problem, namely, there's nothing for mind to do and no way for mind to do it, which is a classical physics problem, and it's true in classical physics. The poised realm affords an answer. The poised realm appears to be real. Patents are pending. There's more experimental demonstrations of it, and so on. So please take that in. It's written up in a paper called Answering Descartes, Beyond Turing, which is online on Physical Archives, and it's online ECAL 11, and it's been published in a book whose reference I don't have right now. But all you have to do is Google Answering Descartes, Beyond Turing plus Kaufman, and you'll find the paper. Okay, now I want to get to the problem of free will. Again, let's state the standard problem. If the brain is a Newtonian classical physics system, it's got entailed deterministic dynamics, just like the billiard balls. So there's nothing for mind to do, nor any way for mind to do it. So we cannot have a free will at all, let alone a responsible free will. Okay? That's the standard problem. If, as I've already said, we invoke quantum mechanics, even in the poised realm, a quantum measurement event has the following property. Quantum mechanics says the Schrödinger wave propagates a whole bunch of waves. The Born rule says square the amplitude of each wave. That squared amplitude is the probability that when you measure the system, that wave will be the one that is measured in the measurement outcome. But this is essential. There is nothing whatsoever that tells you what the specific outcome is. I mean, for example, if you're measuring an electron spin that could be up or down, there's a squared amplitude or probability for being up, and there's a squared amplitude for the probability of being down, and that's all we know. There is no way that we know of to deduce the actual outcome of any single quantum measurement. So hold that in mind. I'm going to come back to it. It's essential for what I want to say later on. But that means the following. If there's no way to deduce the outcome of a single quantum measurement, then that outcome is not entailed at all. Unlike Newtonian mechanics, where you can deduce the consequences, and like a Turing machine, where you can deduce the next state of the Turing machine from the current state, because Turing machines are a subset, discrete state, discrete time of classical physics. Okay, so meanwhile, back to free will. Not only can we not determine the outcome of the quantum measurement, it's entirely random, with some probability of the spin being up or down. Therefore, if I'm walking down the street and a quantum event happens in my mind, and I pick up a frying pan and I hit the little old man and kill him, we might want to say that I have a free will, but it can't possibly be a responsible free will. It's an entirely random event, whether it's spin up or spin down. And spin up, I kill the man, and spin down, I don't kill the man. So we have the start of a free will, but not a responsible free will. Okay, now I'm going to go on to the main part of my talk, which I've never talked about before. It's long, and I think it's right. But whether it's right or not requires all of us to now first hear what I've said, and then think carefully about whether or not what I've said is correct. I believe it's correct. I may be entirely wrong. If it's correct, it changes physics in very interesting ways. So be patient with me, because what I'm going to tell you, if true, does in fact change physics. So there are a bunch of steps. Bear with me. First, the Schrödinger equation is a linear wave equation, and it is set equal to a classical potential V, the Hamiltonian, and then the physicist generally supplies some boundary conditions, like a box, or whatever the boundary conditions are. And given that, what one does, one integrates the Schrödinger equation to get the entailed dynamics of the Schrödinger wave equation, that solution depends on both the Hamiltonian, the classical potential, and it depends upon the boundary conditions. Just like the billiard balls bouncing on the table depend on the boundary conditions, and the total potential, in effect, the total potential energy is the quantum analog of kinetic and potential energy in classical physics. Okay, so that's what you do with the Schrödinger equation. Now, the next statement, I'm on 3, is if you change the boundary conditions or the Hamiltonian of a classical system, or at least a classical for all practical purposes system, you change the possible behaviors of the quantum system. So let me go back and be explicit. Given the boundary conditions for the time-independent Schrödinger equation, one gets standing wave solutions, which are called eigenfunctions, like a vibrating string on a guitar, and the boundary conditions, just like the two tied down ends of the string, determine the patterns of vibration of the guitar string, the eigenfunctions, and if you change the boundary conditions, like putting your finger up 1 fret or 2 frets on a guitar, you change the tones and the overtones of the guitar string. You change the eigenfunctions by changing the boundary conditions. If you change the boundary conditions of a quantum system, you change its modes of behavior too. Okay? So that's just true. Also, if you change the Hamiltonian, you change the behavior of the quantum system. I want to give you a concrete example in the real world, unless you think I'm just talking philosophy. Physicists really make effectively classical physical apparatuses, and they measure quantum systems with them. A famous example is called the Stern-Gerlach apparatus, and it's used to measure whether an electron is spin up or spin down, or spin left or spin right, or any other axis you want. Here's the critical points. First of all, physicists really make Stern-Gerlach apparatuses. So the universe is such that physicists can make real Stern-Gerlach apparatuses, and they can really test quantum systems and test quantum mechanics, and they get the right answers that's confirmed quantum mechanics. Point 1. Point 2, when the physicist decides to measure spin up or spin down for the electron, he sets the Stern-Gerlach machine a particular way, and that particular way includes the Stern-Gerlach apparatus constituting boundary conditions on the behavior of the quantum system, and perhaps the Hamiltonian. I don't know that part. If the physicist decides instead to measure spin left or spin right, the physicist changes the boundary conditions in the Stern-Gerlach apparatus, and the changed boundary conditions now yield the fact that the quantum behavior of the electron will reveal upon measurement spin left or spin right. So the critical point here is that in the real physical world, physicists make instruments, here are the Stern-Gerlach apparatus, and they change the behavior of the quantum system from spin up versus spin down to spin left versus spin right by changing the effectively classical boundary conditions of the Stern-Gerlach apparatus, and those boundary conditions are the boundary conditions of the quantum system and change how the quantum system behaves. So the main point to take in is we can in fact change boundary conditions, and it changes the behavior of the quantum system. Hold that. It's going to be central. Okay. Now, the next thing to notice is that the Stern-Gerlach apparatus is, in a deep sense, a stable structure. It sits on the table for years. So it's a stable structure. It's really sitting there. It's made out of whatever it's made out of. The notion of a stable structure is going to be essential to what I want to talk about. The next point is the following. Some quantum measurements do not, and some do, yield stable structures. Let's take a look first at quantum measurements that do not yield stable structures. So in quantum electrodynamics, there are electrons that emit and absorb photons. The absorbing and emitting of photons are quantum measurement events, but the Schrödinger wave keeps propagating unitarily all the time, and no stable structures are made. I think the Schrödinger equation propagates unitarily. I may not be right about that. But in any case, no stable structures are made. All you have are electrons and photons. Now consider the famous two-slit experiment, where you've got two slits in a little barrier, and you send a single photon through it, and the photon does whatever it does. In quantum mechanics, you actually have to say that it simultaneously goes through both slits, and therefore you have to say that it simultaneously does and does not go through the left slit. I'll come back to that. And then it hits an old-fashioned silver halide film emulsion as the photodetector. Okay? When it does, if you developed the film, of course, you will see a spot where the photon hit. That's how people did the two-slit experiment until we had CCDs. With CCDs, you get an electrical potential. Okay? The single photon goes through the two-slit experiment and hits the film emulsion. When you develop the film emulsion, you find a spot on the film emulsion. That's the spot, that's the famous spot that is part of the wave-particle duality, where the spot is the particle. And if you let a lot of photons go through, you get the interference pattern. Now, the important and essential point I want to make about the spot on the developed film is that it, too, is a stable structure. The spot is present on the developed film for a month or a year or 10 years. It does not go away. So it's a stable structure. So the spot, when it appears, is a quantum measurement event. The single photon is hit and the spot is there. That's a quantum measurement event, but it has created a stable structure, unlike quantum electrodynamics, where electrons absorb and emit photons, but no stable structure is made. So I want to make a fundamental distinction between quantum measurement events that do not make stable structures and those that do. The spot is a stable structure. That's a fact of the physical world, and it's true. Okay? Now the question is, why is the spot stable? And the answer is quantum mechanics itself. Because what's happened is that when the photon hits the film emulsion, chemical bonds are formed and broken, and because of the Pauli exclusion principle, no two electrons in the same atom can be in the same quantum state, and in fact no two nucleons in the same atom can be in the same state. Therefore they have to be in different states with different energies, and to get from one energy to another takes a quantum event where you absorb or emit some quantum of energy. Because of those energy jumps between different quantum states, a given state in a given chemical bond is stable and lasts for a long time, like the structure of the DNA molecule. This was Schrödinger's point in What is Life? He said the gene has to be due to quantum mechanics and stable chemical bonds. It's not due to statistical mechanics, he argued. The other thing to point out here just briefly is coal, black coal, is also a stable structure. It lasts for millions of years, but it's not a low energy state. You can prove it by burning coal and it gives off heat, okay? So the stability of a chemical bond, or the chemical bonds in the spot on the photodetector, is stable, and the stability is due to quantum mechanics itself. Okay, so that's the next point. So the next point is the Stern-Gerlach apparatus is a stable structure also, just like the spot. And remember that with the Stern-Gerlach apparatus, which is a stable structure due to chemical bonds and quantum mechanics, the physicists can change the boundary conditions and change the behavior of the electron from spin up, spin down to spin left versus spin right. So if the physicist changes the boundary conditions of the stable structure of the Stern-Gerlach apparatus, he changes the behavior of the quantum system from spin up, spin down to spin left, spin right. It's exactly the same thing with the spot on the screen on the photodetector. If the spot is exposed and is, say, white, photons that hit it will behave differently than if there is no spot. So the spot has changed the behavior of the quantum system of which it's a part. Now let's ask how the spot is a part of the quantum system. Well, it's both a boundary condition, like the Stern-Gerlach apparatus, and conceivably it affects the Hamiltonian of the quantum system. Now I'm ready for my main argument. A single quantum event, a single measurement event, let's take the Copenhagen interpretation of quantum mechanics right now. Again, remember what you do is you take the quantum Schrödinger wave that propagates deterministically and is entirely entailed. Then by the Born rule, you square the height or the amplitude or the modulus of each wave, and that gives you the probability that if you measure the system, that wave will be the one that's measured. But it does not tell you what the outcome of the single quantum measurement will be. The outcome is indeterminate on the Copenhagen interpretation, and we could talk about multiple worlds as well, and it turns out to be the same thing, but requires a little more discussion. So Copenhagen will do us right now. If the outcome is indeterminate, as I've already said, and there's no mathematical formula that you can write down that gives you the outcome, and there is no such formula that anybody knows, then the outcome is not entailed. Remember I said that in Newton, the motion of the billiard balls is entirely entailed by integrating the differential equations. Nothing entails the outcome of the single quantum measurement. Therefore, the spot on the screen is not entailed. It's not entailed at all. It just happens. But here's the next step. The unentailed spot is now a different, this is really critical, it's new in the universe. The spot was not there, now the spot is there. Once the spot exists, it's a new thing in the universe, the spot on the screen, and this new thing is a new boundary condition on any adjacent quantum system of which it's part. So it's just like changing the Stern-Gerlach apparatus boundary conditions from enabling spin up, spin down, or enabling as boundary conditions spin left, spin right. When a spot comes into existence, it changes the behavior of the quantum system as a new boundary condition. But if that spot is unentailed, then it's the spot constituting the boundary condition is unentailed, and therefore, and this is the essential final step, the new possible behaviors of the quantum system for which the spot is the boundary conditions are themselves unentailed. Now, if this is right, it says that when quantum measurements create stable structures, the universe is creating, in single measurements, unentailed new possibilities. They're creating new possibilities. So let me pause to tell you that this is radical and new. It's not part of standard quantum mechanics. In standard quantum mechanics, for example, on the multiple world interpretation, there's the initial condition of the universe, the Schrödinger wave propagates deterministically, and on the multiple world interpretation, every time a measurement event happens, the universe splits, to create multiple worlds. But on any single branch in the multiple world interpretation, the possible branch is already entailed by the initial conditions of the universe and the unitarily propagating Schrödinger wave. Therefore, no new possibilities can arise on the standard interpretation of quantum mechanics. All of the possibilities that can ever arise are entailed by the initial conditions of the universe and the unitarily propagating Schrödinger wave. New possibilities can arise. If I'm right, that statement is wrong whenever quantum measurements make stable structures that are stable in the sense that I've just told you. So I'm telling you new physics. That's point one. Point two, in the multiple world interpretations, any single quantum measurement is unentailed. Therefore, any single branch in the multiple world interpretations is once again unentailed. That's sort of a side point, but I wanted to make it. Now, the next thing to notice is the Schrödinger equation is time reversible. What I just told you is not time reversible. I'm going to go on. I'm going to go on for about 5 minutes. Okay. It's not time reversible. Okay. Therefore, time is real. If I'm right. Okay. So now I want to try to get to a responsible free will in the next few minutes. Okay. And it's the following. Any single quantum measurement is, of course, random. Here's the next idea. Suppose that there is a sequence of events in which a measurement event happens and creates some classical condition. For example, let it be proteins in the synapse of some neuron in the brain that's receiving neurotransmitters. And here's the idea. Suppose that the quantum measurement event, it might be an electron going to an excited state, only slightly alters the boundary condition that was there to a new boundary condition. Then the result is that the new quantum system has very similar behaviors to the old quantum system, and so on over a succession of slight alterations in the boundary conditions, or slight alterations in the Hamiltonian. What that creates is the following. Any single quantum measurement is random, but since the boundary conditions in Hamiltonian only change slightly, over a sequence of such measurements, the sequence is not random. Therefore, we now have the basis for, ontologically, the start of a responsible free will. It is on this argument that the sequence of measurements, by the sequence of slight changes in boundary conditions or slight changes in Hamiltonians or both, yield a non-random sequence of measurement outcomes, and therefore we have the basis for an ontologically real free will. So I hope I've now given the basis for answering Descartes how mind can act on matter by coherence and recoherence. And by the argument I've just given you, I hope I've given you the start of that we can have non-random behavior, namely the sequence of measurement events, not any single one. Therefore, the ontological basis for a possible responsible free will. Let me close by saying what this does not do. Well, I want to say two things. It's about consciousness. Nobody knows what consciousness is. In answering Descartes beyond Turing, I propose, following Penrose and Stapp, but independently of them, that the conscious experience is associated with quantum measurement. There's experiments we can do to test by selecting on fruit flies to be easily identified and seeing if the mutant proteins do not carry out quantum measurements that the wild-type proteins, the unselected flies, do. So we can test that hypothesis. That still won't tell us what consciousness is. I do not think there's any way from third-person description to get to experience what consciousness is, to qualia. I think that, and I'll get to now. The next step is, let me repeat the steps that I was saying before, that I think are physically new and can form the basis for a responsible free will. So I may repeat more than we want, and you'll have to edit. I started by saying, discriminating between quantum measurement events that give rise to stable structures, like the spot on the photodetector in the film emulsion, when the two-slit experiment is done and one photon hits the film emulsion and you develop the film, the spot is stable. It's there for years. As opposed to quantum electrodynamics, where photons and electrons are exchanged, but no stable structure is formed. So the next sentence is, but why is the spot stable? And the answer is because of quantum mechanics itself, where because of the Pauli exclusion principle, no two electrons or nucleons can be in the same state in the same atom. So chemical bonds form, and they are in unique quantum states. And to get from one state to another takes an energy jump, absorbing or emitting some quantum of energy. That's why the bond is stable, and that's the point that Schrödinger makes in What is Life? So chemical bonds in the spot are stable, but I point out it's not a low energy structure. Coal is stable for millions of years, but if you burn it, it gives off heat. So it's not a low energy structure. It's stable because of quantum mechanics itself. Then the next point that I made and remake was the following. In the Stern-Gerlach apparatus, it too is stable because it's got chemical bonds in it and because of quantum mechanics. And again, the quantum physicist can change the boundary conditions in the Stern-Gerlach apparatus so that he either gets spin up or spin down to the electron, or by changing boundary conditions, the electron is spin left or spin right. In exactly the same way, spot, once it exists or does not exist, constitutes a new boundary condition that wasn't there in the universe before the spot appeared. And it will change the behavior of a quantum system where it's the boundary condition. For example, photons behave differently if they hit a spot than if there's no spot there. So then the next point was, but the outcome of a single quantum measurement, the spot, is not entailed. There's no mechanism to get from the probability of the outcome of a quantum measurement to the specific outcome of the measurement. So the spot is not entailed. But that means that the spot, in constituting a new boundary condition on the quantum system, is also not entailed as that boundary condition. But that means that the new behavior of the quantum system, for which the spot is the boundary condition, is not entailed either. There are new possibilities that are not entailed. None of it is entailed. There is an entire becoming of ever new possibilities, none of which are entailed. Nothing is entailed in this sequence. If there's a succession of quantum measurement events, new quantum behaviors, new quantum measurement events that become new boundary conditions over some sequence. It's out of that that I'm going to try to make the possibilities for a responsible free will. Then I pause to say that this is new physics. It's time irreversible, so time is real. And furthermore, new possibilities arise because of this interaction of the quantum world with stable structures like the Stern-Gerlach apparatus and spots. That's not how standard quantum mechanics happens, in which, for example, there's a wave equation of the universe, and all that happens is new waves emerge, and they're all entailed. So all the possibilities and all the waves are entailed. And on a multiple world interpretation, when there's measurement events, the universe splits, but all the possible splittings are all entailed from the initial conditions of the universe and the deterministic evolution of the Schrödinger wave. No new possibilities arise in standard quantum mechanics. If what I'm saying is right, standard quantum mechanics is wrong when a measurement event gives rise to a stable structure like a spot, a Stern-Gerlach apparatus, which is of course constructed, but spot isn't. Okay, so this is new physics. Now I want to get to the basis of a responsible free will. Any single quantum measurement is random with respect to its possible outcomes, with the probability given by the Born rule, the square of the amplitude of that wave. But it's random in the sense that it's entirely indeterminate which outcome it is, spin up or spin down, or whatever the possibilities are. Here's the idea. If there are a succession of quantum measurement events that create things like spots that constitute new boundary conditions that enable new adjacent possible quantum behaviors, like the photons hitting the spot. But if the new boundary condition is like the old boundary condition, highly similar to it, then the behavior of the new quantum system will be similar to the behavior of the old quantum system. Therefore, measurements on the new quantum system will create new things like spots, except that I'm going to change it from spots, that are slightly modified boundary conditions from the previous new unentailed boundary condition over a sequence. Now, if we can achieve that, we are going to have a sequence of new boundary conditions, new in the universe, new quantum behaviors, new measurement events that form a sequence, and the sequence itself is not random. The outcome of any single measurement is random, but the similarities in the outcomes is entirely not random. And that is what I want to make the basis of a responsible free will. In place of spots, just imagine what we're talking about are synapses in your brain, that we're talking about postsynaptic protein complexes bind neurotransmitters like GABA and serotonin, and those protein complexes form boundary conditions for the behavior of the quantum world of which they're part. But when quantum measurement happens, minor changes in the proteins take place. For example, some electron might jump to an excited state, or a new chemical bond might form. Then over a succession of these modifications, a succession of very similar boundary conditions and similar new quantum behaviors will happen, and that sequence is not random. Meanwhile, simultaneously, when the protein absorbs an electron, that may change slightly the Hamiltonian of the quantum system. So it changes slightly the behavior of the Hamiltonian. Once again, you get a non-random sequence. So the sequence of behaviors is, each measurement is random and indeterminate, but the sequence is non-random because the boundary conditions in the Hamiltonians are only changing slightly, but the whole thing is totally unentailed. So here we have the possibility of an unentailed sequence of non-random happenings. Since it is unentailed, it can be a free will, and since they're non-random, it can be a responsible free will. One last thing to say on the physics level, there's something called a quantum zero effect. If you measure a quantum system repeatedly, the first measurement puts it in a specific quantum state. If you measure it again very rapidly, you will trap it in the same state. The Schrödinger equation stops propagating. That's known. If you wait a little bit, it flowers new quantum possibilities slowly, quadratically in time. So by timing the interval between measurement events, we can time how many new possibilities arise in the new quantum state, mainly 2 or 4, not billions. Therefore, a system such as this is not only unentailed, it can make slight modifications in the possibilities, and by timing the intervals between measurements, it can tune how many new possibilities arise, and therefore, if you will, how many possibilities the system explores. I think this is an ontological basis for a responsible free will. To summarize the physics of this, the poised realm is almost certainly real. I think it answers Descartes how mind can act on matter. It does so acausally via decoherence, and does so a multitude of times by decoherence and recoherence. And I think we have the possibility of a responsible free will in this non-random sequence of measurement events and new boundary conditions, which still doesn't act on the classical world, for which we need either decoherence or quantum measurement to have effects in the classical world. And none of this tells us what consciousness is, so I'm going to end on that. with following Roger Penrose and Henry Stepp, I independently proposed that conscious experience is associated with quantum measurement. That hypothesis is testable. Here's how. You can anesthetize fruit flies and they're unconscious. You can select on fruit flies for those, you anesthetize them with ether. It's a classical genetic experiment. Select on a population of fruit flies so that it takes very little ether to anesthetize them, or no ether to anesthetize them, and they're unconscious. Isolate the mutant proteins from the normal proteins and ask, do the normal proteins carry out quantum measurements that the mutant proteins do not? Suppose that the answer to that were yes. We would begin to actually believe a scientific hypothesis that consciousness really is associated with quantum measurement. Let me kind of conclude the part about consciousness. That still wouldn't tell us what consciousness is. I think that David Chalmers is right in the problem. No third-person fact will tell us what consciousness is. And I'm going to close with something that's utterly speculative. Suppose we found what I just said, then quantum measurement is either necessary or sufficient for conscious experience. If it's sufficient, then we're driven to say, wherever, no, I want to go back for a second and tell you why I like the hypothesis of quantum measurement being necessary for conscious experience. There's a problem called the unity of consciousness, or the binding problem in quantum in neuroscience, which is how brain areas that are anatomically disconnected can form a unity of experiences of things that are processed in anatomically disconnected areas. In answer to Descartes beyond Turing, I propose that we use non-locality in physics, which is well established, as a means by which entangled quantum variables, say in different anatomically disconnected synapses, when measured, give rise to similar bound qualia that give us a unity of consciousness. It is the happiest answer I can think of to the binding problem in neurobiology and unity of consciousness issue that no neurobiologist has a plausible answer for. And what I just told you is testable. If we were to find that measurement events are associated with qualia, we could find out whether there are entangled measurement events, where the entanglement arises by the exchange of photons that are roughly 300 degrees Kelvin infrared, and I propose a mechanism to do that in the paper. Is it conceivable? Yeah. Is it science? It can be. Right now, is it science? No. We have to test it. So that's why I like quantum measurement as a possible explanation for qualia. It answers the binding problem in principle. Finally, I want to come back to where I just was. If measurement is a sufficient condition for conscious experience, we get anarchism, which it seems to me is conceivable. All of this is utterly speculative. It would say that wherever there are quantum measurement events in the universe, there are conscious experiences. And the question would be, why would the universe bother? And the answer could be in Conway and Cochin's famous strong free will theorem, which proves that for entangled particles, if the experimenter has free will with the Stern-Gerlach apparatus of deciding to measure spin up or spin down versus spin left or spin right, then the electron has exactly, or the pair of electrons have exactly the same free will as entangled particles, and they say the following: nothing in the past of the universe determines the outcome. There is no mechanism for measurement, therefore it's not entailed, as I say. And third, the particles decide or choose. So the absolutely wild thought is particles that are aware, and it's totally wild and crazy, use their knowing to do something. They choose whether or not to be spin up or spin down. If that were right, and that's not far from what Conway and Cochin speculate, where they say the basis of our will must be based on this, plausibly, and so is knowing throughout the universe. I have no idea if that's right. It's not necessarily unscientific. With the fruit fly, we can render it unconscious and and see if it changes its behavior. Conceivably, one could find a way. I have no idea how. If an electron is conscious and aware when it makes a decision to be spin up or spin down by the Born rule, so it's semi-free. If you could wipe out that awareness, would it change its behavior? I have no idea how to do that, but maybe there is a way. To conclude, I think I've given you a physical basis in the poised realm for how mind can have consequences for matter without acting causally on matter, and do so repeatedly via the poised realm, hovering reversibly between quantum and classical for all practical purposes via decoherence and recoherence. And by my last argument, I think I've given you the ontological basis for a unentailed sequence of non-random measurement events that give you the basis for, ontologically, for a responsible free will. Nothing in this gives you any experiential. But I think that this is the potential answer to our question, determinism versus free will, and that says, yes, free will may very well be possible. And I don't see anything wrong with the argument that I've given you about stable structures being unentailed, like the spot, and constituting new unentailed boundary conditions to create new unentailed quantum behaviors over a sequence of similar ones. So, in conclusion, I think I've given you an argument that may, in fact, be physically right. It's new physics, and it may give us the physical basis for mind-brain interactions and the physical basis for responsible free will. Thank you all very, very, very much.